Section 16.5, not 6, section 16.5, surfaces and area. So this section is going to be the springboard to the rest of the course. We have 4 sections left to go, 16.5, 6, 7, 8. And this section will provide a lot of the machinery that we'll need for the big finale for this class. So to kind of set up what I talk about, what I mean when I say, the machinery, the big finale here, let's think about what types of integrals we've thought about in our calculus career so far. So in Calculus 1, we've thought about one-dimensional integrals over straight lines. So the idea here is that I give you the integral from 1 to 3 of f of x dx here. Here is a number line. We're integrating between 1 and 3. This is the region that we're integrating along. In chapter 15 of this book, we kicked it up to two-dimensional surfaces. So two-dimensional integrals over flat surfaces. So the idea here is you could have an integral x runs from 1 to 3, y runs from 2 to 4 of f of x, y, dx, dy. And so the region that we're integrating over, 1, 2, 3, 1, 2, 3, 4, is this region right here in the xy plane. And we're thinking about the xy plane as being part of three-dimensional space. That's a flat surface. In 16.1 and 16.2 then, we went back to one-dimensional integrals over curves. And I might say here, informally, curvy lines. I mean, a line's not going to be curved, so I'm using line here in an informal sense. But the idea here is that we have this curve C, and we're going to calculate a line integral, either a vector or a scalar line integral along this curve C. That's a curvy line in the plane, or in three-dimensional space. So what do you think we're about to do now? Think about what's missing from this chart. For now, we're going to do, so we've done one-dimensional integrals, now we're going to do two-dimensional integrals. So 2D integrals over straight line flat surface, so straight and flat up here, curvy line, so curvy surfaces. And so the idea here in this section is that we're going to, I should say in this section and the next section, maybe you'd want to integrate over a sphere, the surface of a sphere. So maybe this is what's going on. And let me be particular. I want to talk about the surface. So this is different than in chapter 15 when we had an integral over the 3D region that's inside the sphere, including the boundary and the side of the sphere. Now we want to do a two-dimensional integral that's only over the boundary itself, the boundary of the surface here. So this is one example. Another classic example would be a cylinder. And so again, it's just going to be the surface here. Okay, so this is where we're aiming in this section, is to talk about how do we parameterize surfaces. And then later on in this section, we'll talk about calculating out areas, surface areas of these surfaces. I mean, this surface area and this surface area are pretty easy, but we'll have more complicated looking surfaces coming up. And then in the next section, section 16.6, we'll be defining surface integral. So we'll be integrating over these surfaces. So this section is all about the setup. The next section will be more about how to actually apply it for integrals, surface integrals. And then our final two sections of the course, section 16.7, section 16.8, will be on Stoke's theorem and the divergence theorem. And so those will be two very, 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 very big punchlines to the course. They're kind of similar to Green's theorem, which was a punchline in and of itself. It will be good ways to wrap up the entire course. So that's what we have to look forward to.